Hi everyone, welcome to lecture 21 on the expected value of a wager. The objectives for this video are the following. After watching, everyone should be able to, number one, calculate the expected value of a wager, and number two, explain why monetary expected value is not the only thing involved in measuring the attractiveness of a wager. So there's only two objectives this time. The first is a calculation procedure, and the second is an evaluation of sorts of what we're doing when we carry out that calculation procedure. So let's crack on. We'll be looking in this video at this thing called the expected value of a wager or a gamble. It's an application of the probability work we've done over the last two lectures. And in the back of our minds throughout, we're thinking of the expected value of a wager as a measure of how attractive a certain wager or a bet is. We'll see that while expected values go some way towards measuring the attractiveness of a wager, there are other things that are deserving of consideration too. These things are best illustrated using examples, so we're going to go straight into one. So let's suppose we're drawing a card from two randomly shuffled decks without jokers in, so there's just 52 cards. And we draw these cards one after the other. Suppose somebody bets me $10 that I won't get one red card and one black card. Now we set up the problem of calculating expected values using a table, so let me show you how you set it up. First, you list all the possible outcomes in columns. The outcomes we're interested in here are drawing a red card and drawing a black card. So there are four possible outcomes of drawing cards. The first outcome is that we draw a red card from the first deck and a red card from the second deck. R stands for red here. The second outcome is that we draw a red card from the first deck and a black card from the second deck, and here B stands for black. The third possibility is that we draw a black card from the first deck and a red card from the second deck. And the fourth possibility is that we draw a black card from the first deck and a black card from the second deck. The next thing we record in the table is the probability of each outcome. Now, the probability that we draw a red card from either deck is 1/2, because exactly half the cards in each deck are red and exactly half are black. So by the same reasoning, the probability that we draw a black card from either deck is also 1/2. Now, since these events are independent, which you can check as a good exercise using what we've learned last time, we can use the probability calculus rule for special conjunctions to calculate the probability of each outcome. So look at the first outcome, or the first row, where we draw red, red. The probability for a red card on draw 1 is 1/2, and the probability of a red card on draw 2 is 1/2. So by the special conjunction rule, the probability of outcome 1, which is red, red, is 1/2 times 1/2, which is 1/4. So we record that in the table. Now the probabilities for the other outcomes, since the probabilities of the individual events are all 1/2, which is what we've just said, are also all 1/4 by exactly the same reasoning that we've just been through. So we can go ahead and fill those in without any further work. So now we've recorded the probabilities of our four outcomes. The next thing we do is start thinking about the wager that's been made here. The next column we record in the table is a gain column, and in it we list the money we lose or gain for each outcome. The wager that's been made, remember, is a bet of $10 that I won't draw one red card and one black card. So what happens is that I win $10 or I gain $10 if I do draw one red card and one black card. And I lose $10 if I don't draw one red card and one black card, because then the person who I'm betting against was right. Now, looking at outcome 1, we draw red, red. So in outcome 1, I do not draw one red card and one black card. So in outcome 1, I lose $10. And it's negative here to indicate a loss because our column is in terms of gains. Now look at outcome 2. There I do draw one red card and one black card. So in outcome 2 I win $10. Now look at outcome 3. Again, there I do draw one red card and one black card, just in the reverse order to outcome 2. So in outcome 3 I win $10. And lastly, look at outcome 4. There I draw a black card and another black card, so I don't draw one red and one black card. So in outcome 4 I lose $10. Okay, so we've got the gain column done. The final thing we do is calculate the expected values. This is carried out by calculating the expected value of each outcome individually, and then we add up or sum all of the values. To calculate the expected value of any individual outcome, all we do is multiply the probability of that outcome by the gain we make according to that outcome. So let's do that and fill in this column. Let's look at outcome 1. To calculate the expected value of outcome 1, all we do is multiply the probability of outcome 1 happening by the gain we make on outcome 1. The probability of outcome 1 is 1/4 and the gain is negative $10. So 1/4 times negative $10 is a gain of negative $2.50, or a loss of $2.50. Notice that this is exactly the same expected value as outcome 4 because the probabilities and gains are identical in outcomes 1 and 4. So we can fill in that as negative $2.50 as well. Now look at outcome 2. The method is exactly the same. So to calculate the expected value of outcome 2, all we do is multiply the probability of outcome 2 happening by the gain we make on outcome 2. The probability of outcome 2 is 1/4 and the gain is $10. So 1/4 times $10 is a gain of $2.50. And the same expected value occurs in the case of outcome 3 because the probability and the gain is the same there as in outcome 2. So we can fill that in as $2.50 as well. So now we've filled in this last column. And I said the last thing we do is sum, or we add up, all the expected values over all the possible outcomes. So we just add all the values in the expected value column. And when we do that, we find that they all cancel. Minus 250, add 250, add 250, add minus 250 gives you 0. So the expected value of this wager is $0. This is a special type of wager which we'll make a definition for. We say that a wager with an expected value of $0 for each person involved in the wager is a fair bet. We calculated the expected value for ourselves, of course, not for the other person who we're betting against. But in this case, because we win what they lose, and they win what we lose, the expected value for the other person is also 0, so the bet is fair. There's a certain symmetry to this situation. We could check that, of course, by calculating their table too. It would look very similar, but not quite the same as the one we just constructed. Now, of course, there are also wagers that aren't fair, so let's have a look at what one of those would look like. Let's suppose again that we're drawing a card from 2 randomly shuffled decks without jokers, one after the other. Suppose this time though that the wager changes. So suppose this is the new wager. My opponent will give me $100 if I get 2 black cards, and I will give them $1 if I don't. To calculate the expected value, we go through exactly the same rigmarole, so let's set up the possible outcomes first in a table. The outcomes are the same: red, 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 black, black, red, and black, black. The next thing we do is list the probabilities for each outcome. Now, since these are exactly the same as in the first example, we get those for free here. They are all 1/4 again. And the thing we did after that was list the gains for each outcome. Now, the gains have changed here because the wager has changed. The wager, look on the screen there, is this. My opponent will give me $100 for 2 black cards, and I will give them $1 otherwise. So let's pause for a question. So what we should have is -1 for outcomes 1, 2, and 3, because in those outcomes I do not draw 2 black cards, so I would give my opponent $1. In outcome 4 though, I do draw 2 black cards, and so according to the wager, I gain $100. So in the last row of the gain column, we should have 100, or plus 100. The next thing we do is calculate the expected value for each outcome by multiplying the probability of each outcome by the gain for each outcome. So here is another question. We should have the following. Outcome 1 has a probability of a quarter and a gain of -1. So 1/4 times -1 comes to minus $0.25 or minus 25 cents. Outcomes 2 and 3 are exactly the same, so we can fill those in without any further calculations. Outcome 4 has a probability of a quarter and a gain of plus $100. So 1/4 times 100 is $25. The final thing we did was sum up the expected values for each outcome, so let's do that again and calculate the total expected value for the wager. So here is another question. Adding those individual expected values up, we find that it comes to $24.25. So this we see is not a fair bet. It's favourable to me because I'm expected to win. What's more, since again I win what my opponent loses and they win what I lose here, the expected value for my opponent is minus $24.25. So the bet is not only favourable to me, but it's unfavourable to my opponent. Okay, so the types of examples we've seen here, you'll see again on the assignments, so make sure you're familiar with the procedure for calculating expected values. We'll explore some more interesting wagers in the assignments as well, where things get a little more complicated. But what we've been through here are all the tools you'll need to answer those questions. Now, I want to say a little word about what we've calculated, this numerical answer, the expected value of the wager, and what this actually means. We can think of what it means as something like this. Let's suppose I make the wager of either example we've looked at, and I make this many, many times. And suppose that over these many times, the distribution of results corresponds to the probabilities. We get 2 red cards 1/4 of the time, a red then a black 1/4 of the time, a black then a red 1/4 of the time, and 2 black cards 1/4 of the time. Then the expected value of either wager we've looked at will be equal to my average winnings on that wager, so the total winnings divided by the number of wagers I've made. This is all the expected value, i.e. the number that we've calculated means. It's the average winnings over those wagers. Okay, now I said at the beginning that there are other things that are deserving of consideration too when we talk about calculating the attractiveness of a wager. So let's finish up this video by talking a little bit about what those things might be. There are 2 things that are deserving of consideration. One is risk, and the other is real-world value. Let's look at risk first. Now generally it might seem that you'd want to accept wagers with a positive expected gain to yourself and reject those with a negative expected gain to yourself. And if you're offered a choice of wagers, it seems reasonable to choose the one with the highest expected value. However, assertions like this assume that there is no positive or negative value associated with risk itself. Suppose you're given 2 fair bets, but your stake in one is $1 and your stake in the other is $100. The expected value is the same in each one because they're both fair. But if you're someone who wants to avoid risk as much as possible, then you would surely prefer the $1 stake to the $100 stake. And in that case, we say that you're assigning a negative value to risk itself. If, on the other hand, you enjoy taking risks for their own sake, you might prefer the $100 wager, in which case you'd assign a positive value to risk itself. And all this is to say that while expected value is a major factor in determining the attractiveness of a wager, it isn't the only thing that matters. The positive or negative values assigned to risk itself must also be taken into account. Now, another thing those assertions we made before assume, where you accept wagers with positive gain, reject those with negative gain, and you prefer wagers with the highest expected value, is that gains or losses of equal amounts of money represent gains or losses of equal amounts of value to the individual involved. This assumption is sometimes phrased as saying money has a constant marginal utility. However, this assumption is quite often a bad one to make. If someone is poor, for example, a loss of $1,000 to them might mean everything. Perhaps they can no longer afford food to eat. In this case, the real loss of $1,000 is much greater than, for instance, the real gain of winning $1,000. And if you were someone in that situation, it seems foolish to accept something like an even money bet of $1,000 on the flip of a coin. In monetary terms, such a wager has expected value of 0, but in real world terms, the expected value is negative. Its real world value is much lower than its monetary counterpart. So in looking at expected value, you have to take care and see whether the monetary gains and losses accurately reflect the real gains and losses to the individual involved. Now, that brings us to the end of this video. I just want to stress again that although the problems in the assignments on this material contain some new looking concepts, you've got all the tools you need right here to apply yourself to them and solve those problems. Math, after all, which is what we're doing at this point, is not a spectator sport, and sitting down and doing it is how you get good at this stuff. The problems themselves are going to be especially useful for the chapter test on this material, so I highly encourage you to persevere with them, even if they don't look so straightforward. So next time, we'll look at Bayes' theorem, which is one of the most important theorems in the probability calculus, and a real kind of pinnacle of all the stuff we've seen in this course so far, so an important topic. We'll prove the theorem, and we'll apply the theorem, so have a go at your self-reflection questions, and I'll see you all next time.